All right, let's talk about one of the first big decisions you have to make in almost any machine learning project. It can feel like it's going to make or break the whole thing. We're going to demystify that choice. Do you go with a simple, straightforward linear model, or do you jump straight to a powerful tree-based one? Let's dive right in. So, picture this. You just got a new project. A fresh data set lands on your desk. And that first question just hits you, right? Where do I even begin? Should I start with a simple, reliable linear model? Or should I just go for the big guns, like a tree-based ensemble? Well, over the next few minutes, we're going to build a super practical framework to help you answer that exact question every single time. Okay, so your first move, and honestly, this is a real pro tip. It's not to build the most complicated, fancy model you can think of. Nope. The smart move is to set up a simple, rock-solid baseline. Think of it as your benchmark. You have to be able to beat it, and it makes sure you're not just adding complexity for complexity's sake. And that's why linear models are just the perfect place to start. I mean, why? Well, for one, they're incredibly easy to interpret. The coefficients literally tell you, hey, for every 1 unit increase in this feature, the outcome changes by this much. They're also lightning fast to train and to get predictions from. Plus, they're great with sparse data, like you get with text analysis. And get this. In some industries, like finance, their transparency isn't just a nice-to-have, it's an actual regulatory requirement. But, there's a catch. Linear models assume linear relationships. The world isn't always a straight line, right? So what happens when your data just doesn't play by those rules? Well, that's our cue to step into the world of decision trees. Right? So here's the crucial question. What if the patterns in your data are way more complex? What if you've got these intricate, hidden interactions between your features? This is where tree-based models just absolutely shine. They're literally designed to find and capture all those non-linear relationships automatically, so you don't have to go through the headache of trying to engineer them by hand. Okay, so how on earth do they learn all these complex patterns? It all boils down to this concept called Gini impurity. The easiest way to think about it is like a messiness score for a group of things. If the score is 0, it means everything in that group is the same. It's perfectly sorted, or what we call pure. The tree's whole job, its entire goal, is to keep asking questions, making splits that create the purest, most sorted out groups it possibly can. And that leads us straight to the rule it follows. At every single fork in the road, the tree looks at all the possible ways it could split the data, and for each one, it calculates something called information gain. Then it just picks the one split that cleans up the data the most. It's basically asking itself, which question can I ask right now that will give me the biggest possible reduction in all this mess? But here's the catch. A single decision tree, if you just let it do its thing, will keep splitting and splitting until every single leaf at the bottom is perfectly pure. Now, it might sound great in theory, but what it really means is the tree has basically just memorized the training data, including all the random noise and weird quirks. And that's bad because it means it won't generalize well to new data it's never seen before. We have a name for that: overfitting. So what's the solution? How do we get all that power from trees without them just overfitting like crazy? Simple. We use ensembles. Instead of relying on one single kind of flawed expert, we trust the collective wisdom of a whole diverse committee of them. So there are two really brilliant strategies that make these ensembles work. On one side, you've got bagging. The best way to think about this is like you give the same tricky problem to 100 different analysts, and then you just average all their answers together. This is amazing for reducing what we call variance. It means your final model isn't going to be super sensitive to the weird little quirks in your training data. Then on the other side, you have boosting. This is totally different. It's more like building a relay team of specialists. The first model makes a guess, then the second model's entire job is to focus on fixing the mistakes the first one made. Then the third model fixes the second one's mistakes, and on it goes. This step-by-step approach is an absolute powerhouse for reducing bias, which just makes the model fundamentally more accurate. Random forest is probably the most famous example of bagging, and for good reason. It builds hundreds of these decision trees, but there's a really clever twist. Each tree gets trained on a random little chunk of the data, and at every split, it's only allowed to look at a random handful of features. It's this dual randomness that's the magic sauce. It forces the trees to be different from each other. They're diverse, and so when you average out all their predictions, their individual mistakes tend to just cancel each other out. What you're left with is a super robust, low-variance model. Now, don't get me wrong, random forests are fantastic. But really, the absolute state-of-the-art for most tabular data problems these days, that comes from the world of boosting. So let's meet the current champions. First up, we have the algorithm that has just dominated machine learning competition leaderboards for years, XGBoost. I mean, seriously, if you go look at the winning solutions on Kaggle for the last decade, you'll see XGBoost's name pop up over and over and over again. It didn't become the industry standard by accident, let me tell you. So what makes XGBoost so powerful? Well, it's got a few superpowers. It uses a much smarter, more sophisticated math approach to find the best splits. It also has regularization baked right in, which means it actively punishes the model for getting too complex, which helps stop that overfitting we talked about. And one of my favorite parts, it can intelligently handle missing values all on its own right out of the box. Okay, but all that power in XGBoost comes at a price. It can be computationally heavy. So what happens if your dataset is just massive and training time is a real bottleneck for you? Well, that's where our next champion, LightGBM, enters the ring. This thing was built from the ground up with one thing in mind: speed. LightGBM's secret is that it works smarter, not harder. See, instead of grinding through every single data point for every possible split, it does this clever thing where it samples the data and it pays way more attention to the examples the model is having a hard time with. It also bundles together features that don't overlap much, which just simplifies the whole problem. All this efficiency means it can build an incredibly accurate model way, way faster than XGBoost, especially when you're dealing with huge amounts of data. And last but not least, we have CatBoost. Now think about real-world data sets for a second. They are so often filled with categorical features, right? Things like country codes, product IDs, user types, you name it. Well, for that specific challenge, CatBoost is an absolute specialist. CatBoost's secret weapon is all about how it deals with those categorical features. It uses this really clever technique called ordered boosting, which cleverly avoids some common traps you can fall into. But the best part? It handles everything for you internally. That means you don't have to do all that manual pre-processing like one-hot encoding. That can save you a ton of time and honestly often results in a better model anyway. All right, we've met the whole lineup. We know the players. So now it's time for the main event, a direct head-to-head showdown to really nail down the key trade-offs. Let's break this down piece by piece. When it comes to handling complex, nonlinear data, trees are the undisputed champion. No contest. But what about interpretability, being able to explain why the model made a decision? Well, that's where linear models are king. Now look at the pre-processing. Linear models can be kind of needy. They want you to scale your features, handle missing values just right. Trees? They're way more low maintenance. But here's a really critical one: extrapolation. Trees literally cannot predict a value outside the range of what they saw during training. Linear models, on the other hand, totally can. So what's the bottom line? You go for a linear model when being able to explain it is the top priority, or you need to predict future trends. You go for trees when your number one goal is just getting the absolute best predictive accuracy you can on complex, messy tabular data. Okay, so with all that in our heads now, how do you actually make the call on your next project? Let's take all this theory and boil it down into a practical, step-by-step guide you can actually use. Here it is, a super simple 4-step framework. Step 1, always, always, always start with that simple linear model. Get your baseline. Step 2, now bring out the big guns. Test a robust tree ensemble, something like a random forest or XGBoost. Step 3, evaluate the performance gap. I mean, did the tree model totally crush your baseline? Or was it just a tiny, tiny improvement? You have to be really honest with yourself here. And finally, step 4. Think about your production needs. Do you need predictions in milliseconds? Is interpretability a non-negotiable for your boss, your stakeholders? And this right here, this quote just perfectly sums up the professional mindset. Look, complexity always has a cost. It costs you in maintenance time, in computation resources, and in your ability to explain it. So unless that fancy, complex model gives you a truly significant, dramatic boost in performance, the simpler, more interpretable model is almost always the smarter choice for production. So, we're going to leave you with one final thought experiment to chew on. Imagine you're facing that ultimate trade-off. Your stakeholders are demanding a model they can actually understand, but your data is just so complex and nonlinear that a simple linear model is just not cutting it. What's your next move? What do you do? Let that one sink in for a bit. Thanks for tuning in.